Good day and welcome to Big Bad Tech. I'm instructor Jim Pytel. Today's topic of discussion is three-phase AC. Our objective is to examine three-phase AC on an introductory level. Three-phase AC is the biggest thing to hit you little kids. Bigger than guns, bigger than cigarettes. Three-phase AC is how electrical power is generated, transmitted, and used on an industrial scale. People unnecessarily fear three-phase AC circuit analysis because they instinctively assume it's 3 times as hard and takes 3 times as long as single-phase AC circuit analysis, but that's not necessarily the case. Do we happen to know that three-phase AC circuit analysis is essentially identical to single-phase AC circuit analysis, only phase shifted? This is to suggest that all single-phase AC circuit analysis techniques we've learned thus far are still applicable, and most three-phase AC circuit analysis scenarios don't require any special skills. This being said, three-phase AC circuit analysis does take a level of organization and visualization on your part. My advice is to simply pick a direction and stick with it. Go A to B, B to C, then C back to A. As long as you remain consistent and don't switch horses midstream, you'll do just fine. As the name implies, three-phase AC is 3 sinusoidal AC waveforms with the same magnitude and frequency, only sequentially offset from each other by a relative 120 degrees. Let's briefly discuss the advantages of three-phase AC and then take a look at how three-phase AC is generated and used. Three-phase AC power presents numerous advantages over single-phase AC power, only some of which I'll mention here. In my personal opinion, the biggest advantage presented by three-phase AC is the establishment of a rotating magnetic field central to the operation of electrical motors. Large motors essentially cannot run without three-phase AC. Additionally, the rotational direction of three-phase AC motors can be quickly reversed simply by interchanging any 2 phases. DC motors and single-phase AC motors, in contrast, have to resort to some undignified trickery or mechanical contrivances to perform the same tasks, and in doing so, suffer some performance degradation. Three-phase AC motors, because they're guided by a rotating magnetic field formed of 3 voltage phases, rotate smoother and exhibit less cogging, which is jerky, step-like movement. In keeping with this smoothness theme, power electronics devices like rectifiers, which convert incoming AC to DC, exhibit notably pulsed behavior when operated with single-phase AC and require extensive work to clean up the output. However, three-phase AC rectifiers produce notably smoother DC output and necessitate less work to clean up the output. Three-phase AC also presents advantages for power distribution and transmission. It may seem counterintuitive, however, a three-phase AC system composed of 3 smaller, thinner, cheaper, and lighter wires can transmit the same amount of power as a single-phase AC system composed of larger, thicker, more expensive, heavier wire. Given the wires in a three-phase AC system are lighter, the supporting structures needn't be as massive nor as expensive. We'll explore numerous three-phase AC applications in the future. Let's now briefly examine the generation process. Consider the act of generating single-phase AC, where a rotating magnet revolves in close proximity to a stationary winding I'll call L1. Let's say the magnet initiates travel as indicated in the diagram and then rotates in the counterclockwise direction. The starting position of the rotating magnetic north pole would be 0 degrees. Stationary winding L1 is physically located at 90 degrees. In its most simplistic terms, a generator is a stick with a magnet on it. If you rotate the stick with a specific torque and rotational speed inside the stationary windings, rotational mechanical power input is exchanged for electrical power output minus losses via the process of electromagnetic induction. As the North Pole approaches winding L1, induced voltage becomes positive and increases in magnitude. In this scenario, we're assuming positive voltage means plus to minus in the counterclockwise direction. When the North Pole is aligned with L1 at 90 degrees, output voltage achieves a positive peak. As the North Pole recedes from winding L1, induced voltage is still positive, yet decreasing in magnitude. When the rotor reaches 180 degrees, induced voltage crosses 0, going negative. As the South Pole approaches winding L1, induced voltage is negative and increasing in magnitude. In this scenario, we're assuming negative voltage simply means a swap in polarity such that plus to minus is oriented clockwise. When the South Pole is aligned with L1, an occasion in which the North Pole is at 270 degrees, induced voltage achieves a negative peak value. As the south pole recedes from winding L1, induced voltage is still negative, yet decreasing in magnitude. At 360 degrees or 0 degrees, the process repeats itself as induced voltage crosses zero, going positive. Given these observations, induced voltage as a function of angular position obviously demonstrates sinusoidal behavior. Given the rotor rotates at a constant speed, angular position is a function of time, and induced voltage can also be plotted as a function of time. Assuming the rotor completes a full revolution every 20 milliseconds, at 5 milliseconds, output voltage achieves a positive peak. At 10 milliseconds, it crosses zero, going negative, and at 15 milliseconds, output voltage achieves a negative peak, and at 20 milliseconds, it crosses zero, going positive, and the process repeats itself. This should be pretty easy to understand. Let's step this process up a notch. The generation of three-phase AC follows an almost identical course. A three-phase AC generator includes two additional stationary windings, L2 and L3, physically displaced from winding L1 by a relative 120 degrees. Given we located winding L1 in black at 90 degrees, winding L2 in red is physically located at 90 plus 120, or 210 degrees. Winding L3 in blue is physically located at 90 minus 120, or minus 30 degrees, which is the same as positive 330 degrees. You'll note winding L2 and L3 are also physically displaced from one another by 120 degrees, where 210 plus 120 is 330 degrees. Winding L2 and L3 are identical in every respect to winding L1, only their physical position on the stator is different. Let's again assume the rotating magnet initiates travel as indicated in the diagram and starts rotating in the counterclockwise direction. The starting position of the rotating magnetic north pole would be 0 degrees. From the perspective of winding L1 at 90 degrees, absolutely nothing has changed, and we should expect induced voltage to exhibit sinusoidal behavior as previously. This being said, it should be noted that while the rotating magnet travels a complete circle, it also interacts with the physically offset L2 and L3 windings. Consider the following counterclockwise rotation sequence. At 0 degrees, the approaching north pole causes induced voltage across winding L1 to cross zero, going positive. At 30 degrees, winding L2 is aligned with the south pole, and induced voltage across winding L2 achieves a negative maximum. At 60 degrees, the approaching south pole causes induced voltage across winding L3 to cross zero, going negative. At 90 degrees, winding L1 is aligned with the north pole, and induced voltage across winding L1 achieves a positive maximum. At 120 degrees, the approaching north pole causes induced voltage across winding L2 to cross zero, going positive. At 150 degrees, winding L3 is aligned with the south pole, and induced voltage across winding L3 achieves a negative maximum. At 180 degrees, the approaching south pole causes induced voltage across winding L1 to cross zero, going negative. At 210 degrees, winding L2 is aligned with the north pole, and induced voltage across winding L2 achieves a positive maximum. At 240 degrees, the approaching north pole causes induced voltage across winding L3 to cross zero, going positive. At 270 degrees, winding L1 is aligned with the south pole, and induced voltage across winding L1 achieves a negative maximum. At 300 degrees, the approaching south pole causes induced voltage across winding L2 to cross zero, going negative. At 330 degrees, winding L3 is aligned with the north pole, and induced voltage across winding L3 achieves a positive maximum. At 360 degrees, or 0 degrees, the approaching north pole causes induced voltage across winding L1 to cross zero, going positive, and the process again repeats itself. In summary, voltage across winding L1 crosses zero, going positive at 0 degrees. It experiences a positive peak at 90 degrees, crosses zero, going negative at 180 degrees, experiences a negative peak at 270 degrees, and crosses zero, going positive at 360 degrees or 0 degrees, and the process repeats itself. In between these key moments, voltage rises and falls as would a sinusoidal function of angular position. Voltage across windings L2 and L3 exhibits similar behavior, only the peaks, valleys, and zero crossings are shifted. Voltage across winding L2 experiences a negative peak at 30 degrees, crosses zero, going positive at 120 degrees, experiences a positive peak at 210 degrees, crosses zero, going negative at 300 degrees, and at an additional 30 degrees, the process would repeat itself. In between these key moments, voltage would again rise and fall as would a sinusoidal function of angular position. Similarly, voltage across winding L3 crosses zero going negative at 60 degrees, experiences a negative peak at 150 degrees, crosses zero going positive at 240 degrees, experiences a positive peak at 330 degrees, and at an additional 60 degrees, the process would repeat itself. In between these key moments, voltage would rise and fall as would a sinusoidal function of angular position. If we compare and contrast the resultant waveforms, we notice something interesting, yet quite predictable. All waveforms have the same magnitude and the same frequency, only they've been phase shifted with respect to one another. The 120-degree physical displacement of the additional windings in the stator has introduced a 120-degree electrical phase shift. All three waveforms can be plotted on the same graph as a function of either angular position or time. This is admittedly a little busy. However, it should be apparent that each waveform is essentially identical, only it's shifted by 1/3 of a full cycle, or 120 degrees. Let's assume each voltage waveform peaks at 311 degrees and repeats itself every 20 milliseconds. A peak value of 311 volts corresponds to an effective or RMS value of roughly 220 volts. A period of 20 milliseconds corresponds to a frequency of 50 Hz. Given each waveform has the same effective magnitude and frequency, only the degree of phase shift really distinguishes these waveforms from one another. Recall that phase shift is a means of relating one or more quantities with reference to another. In order to calculate phase shift, we need to establish a reference. Let's simply assume L1 in black is our reference waveform. Operating under this assumption, L1 can be expressed far more compactly as a phasor equivalent of 220 volts at an angle of 0 degrees. Given waveform L2's zero crossing going positive appears 120 degrees after our assumed reference waveform, it can be said that L2 in red lags L1 in black by 120 degrees. L2 can be expressed as a phasor equivalent of 220 volts at an angle of negative 120 degrees. While it is true that L3 in blue lags L1 in black by 240 degrees, this is admittedly a little clumsy because phase shift is customarily expressed using positive or negative degrees less than 180 degrees. Given the cyclical nature of sinusoidal AC, lagging by 240 degrees is effectively equivalent to leading by 120 degrees. L3 can therefore most efficiently be expressed as a phasor equivalent of 220 volts at an angle of positive 120 degrees. While the combined plot of voltage as a function of angular position or time for the three waveforms is undoubtedly impressive and sure to confuse your non-technical friends and family, the phasor diagram illustrates the most important points far more efficiently. The phasor diagram clearly illustrates all three waveforms have the same effective magnitude of 220 volts, however, exhibit a relative phase shift of 120 degrees between each other. The phasor diagram additionally illustrates another important property, far more efficiently than the plot of voltage as a function of time. If we were to imagine the three phasors not as representations of voltage, but rather three identical forces pulling an object in three different directions with equal magnitude, in which direction does the object go? The answer is nowhere. The three equal forces applied in three equally displaced directions effectively balance each other out. A different analogy might be a hiker traveling three different legs of a trail. If the hiker heads 220 meters at 0 degrees, stops, then heads 220 meters at negative 120 degrees, stops, then heads 220 meters at positive 120 degrees, where is the hiker? The answer is right where they started. Again, the three equal vectors applied in three equally displaced directions effectively cancel each other out. Let's examine other properties of three-phase AC, starting with the generator. Three-phase AC generators place the windings comprising the stator in one of two, technically three, relationships, either a Y or a delta configuration. Before we dive into this section, allow me to caution you to pay attention to the terminology I'm employing here, as it can get pretty confusing rather quickly. Not as confusing as Gabriel Garcia Marquez's novel Cien Años de Soledad, in which 27 of the 32 male characters are named either Jose Arcadio or some variation of Aureliano, but confusing nonetheless because of the similar terminology employed. Let's start with the basics, and then I'll come back to fill in the details. First, we can visualize the three windings as three independent sinusoidal AC voltage sources, each with the same magnitude and frequency, however phase shifted from each other by a relative 120 degrees. Let's use our previous system stats, in which every winding had an effective value of 220 volts. A line is something leading from a three-phase AC generator to a three-phase AC load. A load can also be placed in a wire delta configuration, but to keep things simple right now, let's just ignore the load and concentrate on the windings comprising the generator. Again, a line is something leading from the three-phase AC source to a load. In contrast, a phase is the voltage across an individual winding, often idealized as a source. Here's an important fact. Regardless of the configuration employed, the voltage across an individual winding will remain the same. This being said, depending upon the configuration employed, both ends of an individual winding may or may not be accessible. Additionally, there may exist a differential between lines. Allow me to demonstrate. A Wye configuration pools the assumed negative ends of the windings in a conjoined central node I'll call N for neutral. If three lines lead from this configuration and the central N node is accessible via a fourth wire, this is known as a four-wire Wye configuration. Given the negative ends of the three windings are pooled together in the neutral connection, it should be obvious that line 1 with reference to neutral is 220 volts at an angle of 0 degrees. Line 2 with reference to neutral is 220 volts at an angle of negative 120 degrees. And line 3 with reference to neutral is 220 volts at an angle of 120 degrees. For a four-wire Wye configuration, the line to neutral voltage would be the phase voltage for the windings comprising this generator. But wait, that's not all. If we modify our four-wire Wye configuration by making the central neutral node inaccessible, this is known as, big surprise, a three-wire Wye configuration. While there still exists a differential between a given accessible line and the central node is simply not accessible. This being said, there does exist a voltage differential between the lines. Given the degree of phase shift between the phases, they don't peak and valley at the same time, and we might observe a differential between line 1 with reference to line 2, between L2 with reference to line 3, and between L3 with reference to line 1. We'll examine line-to-line differential in a moment. A delta configuration, in contrast, forms a triangular relationship of three windings, where one winding's assumed negative end stands on the head of another winding's assumed positive end in a continuous chain. This is where it's especially helpful to just pick a direction and go with it. L1's negative is hooked to L2's positive. Let's call this node B. L2's negative is hooked to L3's positive. Let's call this node C. And finally, L3's negative is hooked to L1's positive. Let's call this node A. You'll note not only is a central node inaccessible in a three-wire delta, it doesn't even exist. Given there exists no central neutral terminal, it's essentially nonsense to refer to line to neutral voltage, but rather only line to line voltage. Given winding L1 is between node A and B, it can be said the line-to-line differential between A with respect to B is 220 volts at an angle of 0 degrees. Similarly, given winding L2 is between nodes B and C, it can be said the line-to-line differential between B with reference to C is 220 volts at an angle of negative 120 degrees. Finally, given winding L3 is between nodes C and A, it can be said the line-to-line differential between C with respect to A is 220 volts at an angle of 120 degrees. For a three-wire delta configuration of sources, the line-to-line voltage is the phase voltage, which if you remember correctly is the voltage across an individual winding. Again, for a three-wire delta configuration of sources, the line-to-line voltage would be the phase voltage. Compare and contrast this observation with our earlier observations regarding the four-wire Wye configuration. For a four-wire Wye configuration, the line-to-neutral voltage is the phase voltage. In contrast, for a three-wire delta configuration, the line-to-line voltage is the phase voltage. By all means, pause the lecture and stare at this diagram until you can appreciate this fact. Wye and delta configurations of sources with the same magnitude are not equivalent. You'll additionally note that our earlier observations regarding the summation of phasor equivalent voltages make these configurations possible. 220 volts at an angle of 0 degrees plus 220 volts at an angle of negative 120 degrees plus 220 volts at an angle of 120 degrees yields 0 volts. No differentials exist within the delta itself because the phase shift between the three phases balances the complete system.